everyone! Welcome to part 5 of chapter 17. Today we are going to talk about complex ion formation and look at how they increase the solubility of some otherwise insoluble compounds. Okay, so complex ions. So they're not as complex as they appear to be initially, and so we're going to talk about what they are and how they react. So we've talked about before that transition metals can be Lewis acids, right? And transition metals actually tend to be really good Lewis acids because they have a lot of available orbitals to accept those electrons. They will often bond to one or more water molecules, just in general, to form a hydrated ion. Like copper doesn't really float around as copper ion in solution, it would float around as the hydrated copper ion in solution. Or as you see the example there, silver, right? Silver will, form a covalent bond with two water molecules and will float around as this silver-water complex. Okay, here, water is going to be the Lewis base, and those lone pairs on our oxygen are going to be donated to our silver, and they will form coordinate covalent bonds, which are similar to covalent bonds, just the way that they're formed is a little bit different. But that's why we're seeing that these ions, these complex ions, they don't dissolve in water because they are formed through covalent bonds. Okay, when we have ions that are formed by combining a cation with several anions, or they can be neutral molecules like this water here, we call them complex ions. And again, that would be this guy. This is a complex ion. We have a metal cation combined with neutral molecules here to form a complex ion. So these water molecules are called ligands. And so we have lots of different ligands that can be used. Water is a really common one though, because any metal that we put in water tends to get hydrated and form complexes like these. Okay, so a complex ion has two different pieces. The first piece is going to be a metallic cation. So that's going to be like silver or copper or aluminum, right? Any kind of metal cation. Some are better than others at forming complex ions. And then the other part of it is the ligand. So it's stuff that has been attached to your metal cation through a covalent bond. And these are always going to be Lewis bases. They are going to have available lone pairs, and they will form a covalent bond with an empty orbital on that metal cation. Okay, so some really common ligands that we have ammonia, we have cyanide, and we have water. Another good one is hydroxide, right? But all of these have these available lone pairs that they can donate to that metal cation, right? That metallic cation is our Lewis acid, and these are going to be our Lewis bases, and they will form an adduct. So again, complex ion formation, it's a type of Lewis acid-base reaction where we're having our Lewis acid will be our metal, our ligand will be our Lewis base, and then we are forming coordinate covalent bonds in that Lewis acid-based adduct. Okay. And again, this bond here, these are covalent bonds, so that's why this whole thing stays together when it's in water. It doesn't dissociate because it's not an ionic bond. We're not seeing a transfer of electrons here. We are having that Lewis base donate its electrons to the Lewis acid, but it forms a bond. It doesn't transfer those electrons, it forms a bond between those two atoms. So here's some common metals that form complex ions. A lot of times these are going to be transition metals. Aluminum can also form complex ions, but typically we see these from transition metals. Here's some common ligands. We have neutral ligands and we have charged ligands, but either way they're always going to have an available lone pair that they can donate to that metallic cation. So you may hear me talk about the coordination number. The coordination number is going to refer to the number of ligands that are attached to the cation. So here, if we look at this first example, see this 2? That's telling you that that's the coordination number there. Okay, so don't make this challenging. This is just telling you how many ligands are attached to your metallic cation. We typically have either 2 or 4 or 6 ligands attached to our cation, so those are going to be the most common coordination numbers. All right, so if we were to look at how to write the formula of a complex ion, first you need to figure out what in your reaction is going to be your metal, right? That should be pretty obvious. Identify your metal. And make sure you're not picking something like sodium that's always going to be soluble or potassium that's always going to be soluble, right? It's going to be typically a transition metal or aluminum. And then identify the ligand. We just talked about some common ones. Water, hydroxide, ammonia, those are really common. Those are probably our 3 top ones. And then you're going to find a table. So there's a table, Appendix Table 7 on page 221 of your lab manual. That's a really good table. It actually shows you how the complex ions are being formed. You also have pages A12 and A13 in your textbook that have lists of the complex ions as well as their K values for the constant of formation. Okay, and so those will kind of tell you whether or not a complex ion will form. If I was, say I was reacting calcium and ammonia, and I want to be like, will a complex ion form? Well, I would look at one of these 2 pages and I would see there is nothing that has calcium and ammonia together. There are no complex ions that are showing up on those tables that have calcium and ammonia together. So I'd be like, well, a complex ion doesn't form then because the formula is not on there. But if I looked, for aluminum and hydroxide, I would see, oh, there is one. There's this guy that forms. Okay. So then you'd be like, I can write a complex ion for that one, right? So use this table to see even, the available list of complex ions that can form. When you're trying to figure out if a complex ion will form or not, a really helpful hint is to see if you have an excess of the ligand. A lot of times in this class, I will specify whether you have a small amount of your reagent or an excess of your reagent, right? Maybe you're only adding a small amount of ammonia, or you're going to add an excess of ammonia. Typically, if I'm telling you there's an excess of this particular compound, right, or this particular reagent, that is kind of a hint that it will probably form a complex ion, because typically these complex ions only form in an excess of the reagent. If we just have a small amount of our reagent, then it will typically form that normal double displacement reaction that you can predict, okay? But if you see the word excess, think, I should double check and make sure that there's not a complex ion that's going to form. And then if there is a complex ion that forms, you're going to use the table to figure out the formula of the complex ion. I'm not going to have you memorize any formulas of complex ions at this point. You're always going to be having tables to help you out there. And then when you're writing the formula of the ionic salt, right, so in the overall reaction, you're always going to have the formula of your, central metal ion and then your ligands, and then you're going to put everything in square brackets except for the charge. And so sorry, I've left them off up here. But your metal and your ligands will go inside the brackets, and then the charge will go on the outside of the brackets. And then you'll have some other ions in solution, and you're going to use those ions to balance out the charge. So in this particular example, I had some chlorines floating around, and so this is a 2+. So I'm going to add on 2 chlorines because each one of those have a negative charge, right, in order to balance out the charge of my complex ion, okay? Because remember, when we're writing these balanced chemical equations, we need to write them as a salt. They need to be neutral. Okay, so we can't have any charges left over. So any available charges, we'll go ahead and we'll put them together to make a salt. This will still be aqueous though. So when we put this in water, it will still break apart into the complex ion and the chlorides. We just need to be able to write it, together. Here I've used chlorides to balance out my charge because my complex ion was positively charged. If you had something like the one at the top, you might balance that out with a sodium because it's negatively charged. Okay, you're just going to have to see what else you have in solution. All right, let's go ahead and try some. So this says, write the molecular, the total ionic, and the net ionic equations for the reaction between zinc nitrate and a small amount of ammonia. So again, typically when I tell you that there's a small amount of ammonia, then you're going to predict the double displacement product. So we would write our molecular equation first. So we have zinc nitrate, and we have ammonia, okay? And so here, I've written ammonia as ammonium hydroxide, and I do this a lot of times when we are writing, especially the double displacement reactions, to remind myself that ammonia reacts as a base. And ammonia exists in solution as ammonium hydroxide. This is actually how it exists really in solution. It's been hydrated, okay? It doesn't exist really as NH3. So writing it this way allows me to see really easily that it's going to produce the hydroxide when I do the double displacement reaction. I want you to be very careful though. When you write the net ionic equation, And when you split ammonium hydroxide does not split as an ionic compound because it's not, right? It is ammonia and it is water. So when I split up ammonium hydroxide in my total ionic equation, right, I need to split it into ammonia and water, not into ammonium and hydroxide. So be really careful there. If that's going to confuse you, then in this reaction up here, just write 2 ammonia plus 2 water. And don't even bother with the ammonium hydroxide thing. Just remember that ammonia typically produces hydroxides because it's a base. Okay. So then we write out our total ionic equation. And again, make sure you split ammonia into ammonia and water. And then we'll cancel out our spectator ions, and we can write our net ionic equation there by bringing everything else down. So as you can see, right, ammonia turns into ammonium in this. Had you written it incorrectly and split this into NH4 plus and OH minus, you would accidentally have canceled out this NH4 plus with this one, and your net ionic equation would be wrong. So be really careful, don't do that. Okay, split it into water and ammonia. All right, let's try another one. So this says, write the molecular, the total ionic, and the net ionic equations for the reaction between zinc nitrate and now an excess of ammonia. So again, like I was saying, when I say that there's an excess of ammonia, that should, cue you in, be like, hey, maybe complex ion forms. Let me check it out. And it's a good idea in this class to keep that list handy anyways, because these complex ions can form, and you may not even be aware of them because you don't know which ones can form. So keep it out as possibilities for these reactions. So here's our molecular equation. So the molecular equation looks the same on this side, but you'll notice this is different. So if we look at one of those tables, we will see that there is this species, okay, is a complex ion that can form between zinc and ammonia, okay? So when we have this and we have an excess of ammonia, that means we're dumping in a ton of ammonia molecules. And once we do that, right, those start replacing the hydroxides, and instead they will bond onto the zinc as the ammonia, because zinc has a greater affinity for ammonia there than it does for hydroxide. So the ammonia can go in and replace those hydroxides that we had before. Okay, so now it's forming this, and you'll notice I have these nitrates because we had nitrate in solution, and this is a 2+, so I need to balance that out. So I've added on these 2 nitrates to balance that positive charge. Okay, and then everything else that's left, I kind of added that all up, and we've got 2 waters left over. Okay, so when we write, there's another way that we could have written this. So since we have an excess of ammonia, we don't need the hydroxides in our reaction like we did before. We kept the hydroxides and that water in there before like this to help us out when we wrote the formula for the hydroxide, because it kind of reminds you again that ammonia will act as a base, and it will act as a base because there's water present. When we have this reaction, we don't need that water to produce those hydroxides. So we don't need to write ammonia as ammonium hydroxide when we have an excess of ammonia. You totally can, I've showed it above, but you can write it this way now because we don't need that water in there to produce the hydroxides. Either way, totally fine. But depending on which way you wrote it, your total ionic reaction will look different. So this is for the first one. Again, remember to split your ammonium hydroxide into ammonia and water, not into ammonium hydroxide. And then we've got our complex ion here. Again, that stays charged and stays together and is charged. And then we've got our nitrates and our water. So then we can cancel out all of our spectator ions. And as you see, the waters cancel out because we didn't need them to produce those hydroxide ions. So you could have written it this way had you chosen the bottom one, where we just have the ammonia, and then you see the rest of the reaction there. Either way, those nitrates will cancel out, and we'll get the same net ionic equation either way. Okay, and it will show the formation of that complex ion. So the zinc and the ammonia to make our compound there, our complex ion. Okay, so like I was saying, with the hydroxides and the ammonia, if a ligand is added to a solution that forms a stronger bond than the current ligand, then it will replace the current ligand. So when we had this last reaction, right, we were adding zinc and we had a small amount of ammonia and it was making the hydroxide. And then when we added excess ammonia, the ammonia took the hydroxide's place and now bonded to the zinc. So the ammonia is going to form a stronger bond with the zinc than the hydroxide does, which is why it replaces it. Okay, so like here we have silver. We have a hydrated silver ion here. And most, like I said, most metals, when you have them in water, will exist as these hydrated complex ions. But when we add ammonia, right, ammonia is going to form a stronger bond with the silver than the water does, so it will replace it, and now we have the silver ammonia complex ion. Okay, and a lot of times, like I've said, we don't usually include the water here because we just assume it's in an aqueous solution. We're going to go ahead and assume that it's hydrated. So a lot of times we'll just write the metal ion and that it's aqueous, and that implies this. It just simplifies our equation a little bit, so we're not having to write water all over the place. Okay, so you've been seeing these double-headed arrows. And so, you know, that should imply that we have an equilibrium. And whenever we have equilibriums, we have K values, right? We've learned all kinds of K values. And so now we get another one. Now we have the formation constant, okay? And so this will be for the formation of the complex ions. So this will be the reaction between an ion and its ligand to form the complex ion, and that's the formation constant, okay? But it's going to be written the exact same way. It's always going to be products over reactants, okay? And they're always going to be raised to the power of the coefficients. So here we've got, you know, our complex ion on the top, we've got silver on the bottom, we have ammonia on the bottom as well, and it's been squared because our coefficient is 2 there. So the rules all stay the same. And again, don't include any solids, don't include any liquids, right? All of the rules are exactly the same for this formation constant. Now we've just learned how to write it for a complex ion. So here are a bunch of complex ions. There are more. Again, look at the table in your textbook, look at the table in your lab manual, right? There are lots of complex ions. We're mostly going to deal with the ones that have cyanide, ammonia, some with the thiosulfate. Hydroxides are really common, right? So these are them. You're not going to be asked to memorize them. I'm not going to ask you to memorize the K values. Those will be provided. You just need to know how to use this information to solve the problems. Okay, so speaking about problems, let's go ahead and try one out. So this says 200.0 milliliters of 1.5 times 10 to the minus third molar copper nitrate is mixed with 250 milliliters of 0.2 molar ammonia. And I want to know, what is the copper concentration at equilibrium? So the first thing we need to do is figure out what forms, right? And so if you were normally writing this reaction, copper nitrate and ammonia, you might go ahead and predict that this would form the copper hydroxide. So the reason it doesn't form copper hydroxide is because we have an excess of ammonia. And you may be looking at this and say, well, I don't see an excess of ammonia, right? It doesn't say an excess, but it's implied in these molarities. So if we look at this molarity compared to this one, right? 1.5 times 10 to the minus 3 molar, that's 0.0015 molar compared to 0.2, right? Our ammonia is over 100 times more concentrated than our copper nitrate solution. So that means we have an excess of our ammonia here, and, so our copper nitrate is going to be limiting. So whenever we have an excess of something that's a ligand, that's typically going to imply that we will form a complex ion. So then we need to go find a table and figure out, okay, what forms? So here is our table, right? Again, there's a table in your lab manual and there's a table at the end of your textbook, okay? And so we find what has copper and ammonia. Well, that's this. So our copper is going to form covalent bonds with 4 ammonia molecules. Okay, so that's going to be our complex ion there. So now we can go ahead and write our reaction for what happens using this as our product. Okay, so you kind of want to work backwards. So this is our product, and so if we think about what formed that, we have 1 copper, so there's our copper ion, and then we had 4 ammonias, so there are our 4 ammonias. And you can always double check your work because the charges on each side should balance. We have a total of 2 plus on this side, and we have a total of 2 plus on this side because ammonia is neutral. Okay, and again, we make sure it's balanced. We've got 1 copper, 4 ammonias, we're good to go. So then we can write our Kf expression. Again, it's going to follow all the same rules. So our complex ion will go on the top, and then the metal and the ligand that formed it will go on the bottom. And then this value came from that table. So now, in order to use this Kf, we need to have concentrations. Okay, so we were given concentrations, but those were the initial concentrations. When we mix them together, the concentrations will change because the volumes have changed. So we can use this dilution expression, right, or our dilution equation, in order to find this new molarity. So M1V1 equals M2V2. We can rearrange to solve for M2 for each one of these, and then we'll put the molarity and the volume on the top divided by the total volume on the bottom. It's important to note that you can use milliliters in these equations as long as you're consistent. So as long as you use milliliters on both the top and the bottom, it'll all work out just fine. So then we find our new concentration of our copper, our new concentration of our ammonia, and then we can use them in an ice table, right? We have a K value, we have an equilibrium expression. You all knew that this was leading to an ice table. So let's go ahead and try that out. Here's our reaction. And so we've got our ice table there. We'll put in our initial concentrations that we just calculated, right? And we have none of our complex ion because we just mixed them together. It's like right before we mixed. And so then we have our Kf expression. And looking at our K value here, you can see that our K value is very, very, very large. So that means it's going to form mostly products, right? And so we've seen this type of a problem before, where right now we have mostly reactants, but we should have mostly products. So what we need to do first is we need to assume that this reaction goes to completion. Okay, and we can do this with these new molarities because they're the mixed molarities. You can also do this in moles and then calculate the molarity before, a later ice table or before you use this Kf expression. But since we've calculated our diluted molarity, we can use that as well. Either way. But since our Kf is very, very large, we need to assume that our reaction goes to completion, and then we'll do a second ice table to kind of shift it back towards the reactants to figure out how much is really there. So let's go ahead and start this off. So we would need to figure out which one of these is limiting. But if you look at these molarities, it's kind of obvious which one is going to be limiting, right? So that's this copper. Okay, our copper ion is so much smaller than our ammonia. There's no way our ammonia could be the limiting ion. But you can go through and do the calculation and prove to yourself that that's what it is. But this, by inspection, will just save you a little bit of time because our copper concentration is so small. So we'll use that as our X value. So we'll have minus X on our reactants and, and minus 4X for our ammonia, and then plus X on our products. So then we can add everything straight down. It's important to note that when we add this, right, this value is so small that for significant figures, it doesn't change the concentration of our ammonia at all. So it was negligible compared to our ammonia. And so then, right, we don't really have zero, right? When we do a reaction, we have zero, but it's not really zero because this is an equilibrium, right? So once we do this reaction to completion, we need to do an equilibrium, back the other way to figure out how much copper is really there. Okay, so then we can do our reaction. We can use those values that we ended with, and we can shift it back towards the product. So now we're going this way, right? In this reaction, we went this way. Now we're going back to the left, okay, towards our reactants. So then we can add everything straight down, just like we do normally, and we can plug these in to our K expression. So here again, our K value is very, very large, so we can assume these changes in concentration are negligible, and we can just go ahead and get rid of those. Okay, so all of the same rules we've learned for equilibrium apply, that we've learned before apply now. We're just solving for something different. So now you'll notice X is in the denominator, and that throws people for a loop sometimes. You can solve for this however you like. I like to think that when we solve for X on the bottom, I can just switch it with whatever it's equal to. So like this switches places with this, and we can write, our new expression. Okay, you can go through and multiply both sides by X and then divide both sides by 1.7 times 10 to the 13th. This is what it comes down to. We can just switch those places. And then we can go ahead and solve. And then that would be the concentration of our copper at equilibrium. So we got to do 2 ice tables in this one because, again, we started with mostly reactants. We needed to have mostly products, so we'll do a reaction ice table, and then we did an equilibrium ice table back to figure out how much of that reactant was actually there. So let's go ahead and try another one. This says what is the concentration of this complex ion, right, with mercury when 125 milliliters of 0.001 molar Ki is reacted with 75 milliliters of mercuric chloride. So we have our Kf value there. I've gone ahead and written the reaction for you. It's not as straightforward. So let's go ahead and use that. So here we are, there's our reaction, and I want to know what is the concentration of our complex ion after this reaction. Okay, so we will need our net ionic equation here, because right now we've got a bunch of spectator ions going on. Like if you see the potassiums on both sides, they're just kind of hanging out, right? We've got chlorines on both sides just kind of hanging out. So we're going to go ahead and get rid of those and see what our actual reaction looks like, right? Our net ionic equation. So there it is. So from there, we can write our Kf expression, right? It's always going to be our complex ion over the metallic ion and the ligand. Our ligand in this case is our iodine. Okay, and we have our Kf value. So again, we're going to do exactly what we did before. We're going to determine the concentration of our ions in the diluted solution. So again, that's going to be our M1V1 equals M2V2. And so we can calculate that out. So that'll be our concentration of our iodine, and we can do the same thing for our mercury. Okay. Once we have those diluted concentrations, we can use them in an ice table. So again, we're going to start off just like how we did last time, right? So we're going to plug in our values, and again, we have 0 for our complex ion. And if you look, our Kf value is really big, right? So that means we are going to have mostly products at equilibrium. So that means we need to do a reaction ice table. So if you look, right, it's not as obvious. Like before in the last problem, it was really obvious which one was going to be our limiting reagent. Here, it's not quite so clear. So what I would do is go ahead and calculate which one our limiting reagent is, okay? So we'll take our minus x's, right? We have minus 4x for our iodine, minus x for our mercury, and then we've got plus x for our complex ion. And again, we're going to set that equal to 0. So like if we added this straight down and this went to 0, what would x have to be? So I've solved for x there. And then again, if we added these straight down and that went to 0, what would x have to be? Okay. So then we look and we see which one's smaller. Okay, so the one for the iodine is smaller. So that is the one that we are going to use as our x value. So I've just carried this over from the last page, but here it is. Now I've plugged in that value for x. So then when we add them straight down, we have no more iodine, we've got a little mercury left, and then we have our complex ion. So now, again, what we're going to do is do an ice table to go back toward the reactants, right? Because it's not actually going to be 0 as our concentration of iodine. It's going to be something really small, but it's not going to be 0. So here I've just subbed it out because the way that this would go, right, this would be minus x plus x, and this was 0 and plus 4x, and then when we add them straight down, it's going to be 4x, right? And then these are going to be negligible. So I just went ahead and swapped that 0 out with a 4x. You can keep doing the double ice tables if you want. I just like to save a little time and space because I know how it's going to play out at the end. So then we've got our Kf expression. Sorry, I wrote over it. But this is on the top, right? And then we've got these guys on the bottom. So then we need to get the 4x to the 4th out of the bottom. So again, I've switched it with our Kf value. Okay, and then we can go ahead and when you calculate that, this all calculated here equals 4 times 10 to the minus 31. So we can set that equal to 4x to the 4th. And then, divide by 4, take the 4th root, and then that will be our concentration, right? Or that will be our x value of our iodine, okay? But I don't want our concentration, or I don't want the x value. I want the concentration of our complex ion. So our complex ion is 1.56 times 10 to the minus 4th, but remember we had that minus x piece there. So we can go ahead and use that here, right? We minus x, but you'll see this is a times 10 to the minus 8th time, compared to times 10 to the minus 4. So this is going to be negligible compared to our initial concentration. So that will be our final concentration in our solution. So the reason that we're talking about this, right, is we're going to go into qualitative analysis. And complex ions are really useful in changing the solubility of an ionic compound. Okay, so we have a lot of, insoluble ionic compounds, but a lot of times we can add some kind of a ligand and we can use that to replace what's bonded to our metal and cause that metal to now go into solution. So a really good example is silver chloride. Right? If we react silver nitrate with, say, sodium chloride, we form silver chloride, which is an insoluble solid, right? And it sits at the bottom. It's white. It's really nice, but it doesn't dissolve in most things. It'll just kind of sit there. But we can cause that silver chloride to dissolve if we dump a bunch of ammonia in there. And if we have an excess of ammonia, then we can cause this complex ion to form, and it will redissolve our solid. Okay, so if we add ammonia to a solution that is in equilibrium with our silver chloride solid, then we can increase the solubility of the silver ion, right? Because this complex ion here is essentially removing the silver from the solution. Okay, so say we had a big pile of silver chloride sitting at the bottom of our solution. Okay, and we had a little bit of silver, a little bit of chlorine, right? Not very much, but we had some in solution. If we dump a bunch of ammonia in there, we start to form this complex ion. And to form that complex ion, we had to use up some of the silver. So as we use up the silver in the complex ion, that concentration will decrease, which means that this will shift our equilibrium to the right, which means that more of our solid will dissolve because we've decreased our concentration of our silver, because a lot of it is going to form this complex ion. So here it is in picture form, right? So say we had some silver chloride solid, and then we went and we added some ammonia here, okay? And as we add our ammonia, the ammonia will go and it will react with the silver that's in the solution, okay? And as it reacts with the silver, then it's going to decrease the concentration of silver in solution, which allows more of the silver to dissolve. And if we keep adding more and more ammonia, more and more silver will be removed from the solution, which means more and more solid will dissolve, and eventually we can cause it all to dissolve if we dump in enough ammonia. Okay, so now let's go ahead and work this out mathematically. So we calculated the molar solubility previously in all of those Ksp problems, but we were doing that in water or maybe in a solution with a common ion, right? But now we're going to calculate the molar solubility of our solid in a substance that's going to cause it to form a complex ion. Okay, and so there will be two different reactions going on here. We're going to have one reaction, right, our Ksp reaction, that has to do with the formation of our solid, and we're going to have another reaction going on that has to do with the formation of our complex ion. Okay, so both of these are happening in the same beaker. Okay, and so again, as we add this, ligand, right, we are going to increase the solubility of our solid. So I can prove it to you, right? Here we go. So I want to calculate the molar solubility of silver chloride in our ammonia, and then I want to calculate the concentration of ammonia in our final equilibrium mixture. Okay, so we have two different reactions going on. We have our Ksp reaction for our precipitation of our solid, and then we have our Kf equation for the formation of our complex ion. When we have two reactions going on at once, we call them a coupled equilibrium, okay? And we need to find a K value for this overall reaction that's happening, okay? So we can go ahead and add these equations up. And when we do, the silver ions will cancel out because one shows up on the left and one shows up on the right. And so we can add this reaction down and we can see the ammonia directly reacting with our solid to produce the complex ion, okay? And so that's kind of cutting out this middleman of the silver ion. But now that we have combined these equations, we need to have a new K value that takes into account both of these. So if you'll recall from when we first started equilibrium, when we add together reactions, we don't add the K values, we multiply the K values. Okay, so we're going to multiply Ksp and Kf, and that will get us our new K value, which we're just going to call K at this point, for this reaction. Okay. So now here we go. We have our new reaction, we have our new K value, and we can go ahead and we can calculate our molar solubility. So we're going to do this pretty much the exact same way as we've done before, except now instead of just having our solid on the left, we also have our ammonia on the left. Okay, so we have our initial concentration of our ammonia, but we have 0 of our complex ion and the chloride. Okay, so we're going to go minus 2x because of this 2 up here, and then plus x for both of them on the right, and then we'll add that straight down, just like we normally do. Then we can plug it into our K expression. So again, we're going to have the products over reactants. Nothing has changed. We're going to raise it to the power of our coefficients, and we can plug things in. Okay, so we have our our x times x over our 10 minus 2x. Don't forget the squared from that 2 in front of ammonia. And then we've got this. So now it's times 10 to the minus 3. That's a little bit like, well, the change could be negligible, but it might not be, right? So it's a little bit hard to tell. So whenever I get into this situation, I would solve it a different way if you can, rather than using the approximation. What's nice here, if you'll notice, we have a squared on the top and a squared on the bottom. So a really easy way to get around using the approximation is that we can square root both the top and the bottom and the right-hand side. So when we just square root everything, we'll get x over 10 minus 2x equals 5.5 times 10 to the minus 2. So now we need to multiply both sides times 10 to the minus 2x to get that out of the denominator. And then we can go ahead and distribute it in, combine our x's, and then solve for x. Okay, and that will be the molar solubility of silver chloride in 10 molar ammonia. This is a really good solubility, right? That's a good concentration to be able to dissolve. Normally, the solubility is extremely low for silver chloride, right? It's very insoluble. If you look at our Ksp, right, that should give you some indication of how well this dissolves. So it dissolves much better in ammonia because, that ammonia is forming that complex ion with the silver and causing a bunch of that silver chloride to continue to dissolve. So the last part of this problem asked us to calculate the concentration of ammonia in the final equilibrium mixture. So we'll do that here. We have 10 minus 2x, so our x is that 0.5. So we can go ahead and do 10 minus 2 times 0.5, and that gets us 9 molar. So it's really good that we didn't, use the approximation here because it wasn't negligible, right? 0.5 compared to 10 is relevant, right? It changed our concentration. So it's really good that we didn't use the approximation in this case. All right, let's try another one. This says how many moles of silver chloride can dissolve in 1 liter of 1 molar ammonia. So this is related to our last problem, okay? So, the previous problem, we had 10 molar ammonia instead of 1 molar ammonia, but we'd work through this all the same way, right? We'd still add together our reactions, and these were the same ones we were just working with, okay? And remember, when we add together our reactions, we're going to multiply our K values, and then we can go ahead and make our ice table, okay? Our ice table, we're going to, not worry about our solid. We'll fill in ammonia, minus 2x plus x, and then we'll add everything straight down. We can plug that into our K expression just like we did before. And again, we're not going to use the approximation because, as you saw previously, right, it wasn't negligible. So we're going to go ahead and square root both sides. Since we have squared over squared, we can do that. And then we'll multiply both sides by 1 minus 2x. And then we'll distribute that. And then we can combine our x's and solve for x. Okay. And then it asks how many moles can dissolve in 1 liter of 1 molar ammonia. So we'll just take, our 1 liter, right? And if we look, since we have 1 liter and we have our molarity, right? If we have, moles is usually molarity times liters. So if we take our molarity times 1.00 liters, then we have, moles of silver chloride already. Okay, so since our volume's 1 liter, our molarity and our moles are going to be the same. Okay, so just if it asks you to do this, you're going to go through the exact same process, right, as we did to calculate molar solubility. And then at the end, you're just going to use this volume to convert your molarity into moles. All right, our last topic for today is about metallic hydroxides, or specifically amphoteric metallic hydroxides. Many metal hydroxides are insoluble, like magnesium hydroxide, calcium hydroxide, iron hydroxide, zinc hydroxide. We have lots of hydroxides, but a lot of them are insoluble or have very limited solubility. But all metal hydroxides become more soluble in acidic solution because if you think about our solubility equation here, right, this would be for calcium hydroxide. If we add acid to this, so if we add acid, when we do that, it's going to react with the hydroxides that are present in the solution. And it will remove these hydroxides, right? If we put a 2 here, it will remove those hydroxides as water. And so as we add acid, that is going to decrease the concentration of the hydroxide because it's going and forming water. So as we add acid, we decrease the concentration of hydroxide, which will shift this equilibrium to the right to produce more hydroxides in solution, right? So as it shifts to the right, though, the way that it does that is it causes more of this calcium hydroxide to dissolve, okay? So anytime we add acid to our metal hydroxides, we are going to increase the solubility. But some metal hydroxides can also act as acids, and they can become more soluble in a basic solution, and this is because they are amphoteric. Okay, so they can act as either an acid or a base. So we have some cations listed below that form amphoteric hydroxides. So we have aluminum, chromium, zinc, lead, and tin. Okay, and so let's look at how they do this. So hydrated metal cations will act as weak acids. And the way that they do this is they will, if we look at aluminum, right? Aluminum, again, doesn't float around as aluminum, right? They're always going to be hydrated. All cations are going to be hydrated in water. And so it has 6 attached to it. This, again, you can look up on one of those tables. Okay, and so if it reacts with water, it will act as an acid. And the way that it does that, it will take one of the hydrogens off of one of its water ligands, and it will donate that hydrogen to that water. Okay, and so one of the waters on the aluminum becomes a hydroxide because it's lost one of the hydrogens and it gave it to this water out there. So the fact that it's producing H3O plus tells us that it's making an acidic solution. Okay, so this is how it does it. One of the hydrogens from one of the waters is donated to a different water molecule and produces hydronium ions. If we if we started to add hydroxide to this, so if we added hydroxide to our solution, okay, well, the hydroxide will react with the acid present and it will remove it as water, right? And since we're removing it, right, we're removing our hydronium ions, that will shift our reaction farther to the right, and it will keep producing more acids. So since it's got all of these different water molecules, right, more and more and more of them can act as, can react with water to produce more and more hydronium ions, okay? If we added acid, we can actually push it back the other way and cause it to form more of this species, okay? So it can go either way. It can, lose these waters and make hydroxides on, as a ligand on our aluminum, or it can, gain some. And so when they are equal, right, when we have our water molecules are equal to our hydroxides, right, we can write that just as aluminum hydroxide, which is a really common one we've seen a lot of. And this is because, right, we don't need these waters on here. In all of these instances, we don't need to write the waters because they're going to be implied. Okay, let's look at it another way. So if we have aluminum hydroxide, right, or this hydrated aluminum hydroxide, it can act as either an acid or a base. Okay, if we add acid to this aluminum hydroxide, right, or this hydrated aluminum hydroxide, if we add acid, it's going to react, right, with the hydroxides that are on there, and it will go ahead and form water, right, and it can act in that case as a base. But if we were going to add, hydroxides, right, then it can react with the water molecules on there, and then in this case, our aluminum hydroxide can act as an acid. So since it has both these hydrated water molecules and the hydroxides on there, it can act as either an acid or a base. And so whichever, if we add an acid, it will act as a base. If we add a base, it will act as an acid. This is very much like how water acts as either an acid or a base in the presence of different species. Okay, you just need to know which part of it is reacting with. When we have it, if it's completely hydrated, then it will act as an acid. And if it looks more like this, then it will act more as a base. And that's the end of today's lecture on complex ions. We covered a lot of ground today. We looked at what complex ions are. We looked at how you might look them up in a table to determine what species might form. We've looked at a lot of different mathematical problems that we can do with these complex ions, and especially how they increase the solubility of otherwise insoluble solids or solids with very limited solubility. And then finally, we've talked about amphoteric hydroxides that can act as either an acid or a base, depending on what they're in the presence of. All right, I know that's a lot to take in. You've got a lot of work to do. As always, though, keep practicing, do the problems on the lecture worksheet, and there's a lot of good problems actually on ALEX for this particular chapter. We are going to use these complex ions a lot moving forward, especially as we get into qualitative analysis, because they're really good for dissolving certain, like I said, insoluble compounds. So make sure you're really understanding what complex ions are and how they form and how to do the calculations. As always, if you get stuck, please send me questions if you have them, and I will be happy to work through them. Otherwise, keep working hard, and I will talk to you guys next time.